Welcome to Maker Faire for this interesting session on robots.
So we're here to talk about robots, most specifically humanoid robots, and these two gentlemen who are working on humanoid robots, and I'm a retired humanoid robot guy. And a lot of people wonder why there aren't humanoid robots everywhere. And the analogy that I like to use is C-3PO versus R2-D2. So R2-D2 robots are very, very easy because they're on wheels and they can just drive along on very flat ground. But C-3PO robots, which actually walk, are very difficult. And if you actually watch the original Star Wars movies, you'll never actually see R2-D2 going up and down stairs or stepping over rocks. They cheat that with camera angles and cuts. And C-3PO was actually a human in a bodysuit. So how many senses do everybody in this room think you have? Anybody? 5? Your kindergarten teacher lied to you. You have 21 senses. 3 of those senses are very important for walking. One of them is your sense of balance, which we all know sometimes you lose your sense of balance and you trip and fall. One of them is your sense of proprioception, and your sense of proprioception is knowing where any of your body part is at any given moment. When you wake up in the middle of the morning, you know whether you're sprawled out like this or curled up in a ball like this or whatever. And if they numb your arm for like a surgery or something, you don't know where it is. And it's more than just feeling, it's actually this sense of placement, of knowing where you are. And then you have the kinesthetic sense, which is knowing how to put all of your arms and things in certain places. And your kinesthetic sense is how you walk. And it's also what you do when, if you're pulled over for drunk driving and the cop says, okay, close your eyes and touch your nose. And everybody who's sober can do that. But when you're drunk, you can no longer do that because even though you still have a sense of touch, you've lost your sense of kinesthetics and you don't know how to do that. And so that is the problem with getting robots to walk, and that's what we're here to talk about.
Wow. That was fascinating. I didn't know any of that stuff.
I didn't know anything about English all through high school until I studied Russian as soon as I got out of high school, and I learned more about the English language and grammatical constructs by studying Russian than I ever did by studying English. I knew nothing about the human body until I went to SF State and started teaching humanoid robotics, and I learned all sorts of amazing things about the human body. Like you have 580 muscles, most of which are below the waistline, and most of which control how you walk.
That's fascinating. Well, I've got some hokey stuff to show you.
Hokey stuff, we love hokey stuff.
Gosh, I don't know. I mean, maybe we should start with you. You actually know a lot more about making humanoid robots walk than... Tell us what you're working on.
Okay, so my background is I worked at
First, introduce yourself.
So my name is Gui Cavalcanti. Hello, everybody. I am currently the CEO and co-founder of a company called MegaBots, which makes 15-foot-tall giant humanoid robots. We currently have a robot on tank treads, which is out shooting a giant car kind of as we speak. Out in the MegaBots Autodesk area. It's in the southeastern corner of your map. So go check it out. In a previous life, I worked at a company called Boston Dynamics, which makes like robot horses and humanoids and stuff like that. All hydraulic, all super fast moving. So I'm a mechanical engineer. My focus is on building the systems that are capable of walking and kind of building in sensors and building in all sorts of kind of clean kinematics to allow for proper sensing for walking, which is its own kind of hard nut to crack. But
again, getting back to that kinesthetic sense of knowing where any given body part is at any time.
Yep.
If you watch videos of humanoids that fall down, you'll often see the humanoid laying on its back going like this, because it doesn't know which way is up, which is another one of your senses, is your sense of gravity, which is a real sense, is that you always, no matter what, know which way is up, or actually which way is opposing the gravitational force. And you have to teach a robot that in order to know that when it's fallen over and it's walking, that it should stop and stand up and keep walking.
Yep. So here's the big deal. All right, so robots kind of came from CNC machinery that MIT developed in like the 1950s. So in the 1950s, the whole idea was like, let's make manufacturing controlled by computer. Let's have machine tools cut paths automatically, right? And if you're working on a machine tool and you're working with metal, what you care about is the exact position of the tool, cutting out the right path, making a part that's perfect, right? Like that is what you care about. That's called position control, right? So you are tracing the exact line that you want, you get the part that you want, you're done. The problem is when it comes time to actually make balancing robots, robots that behave like animals, like human beings, like quadrupeds, the world, so in a machine tool environment, the machine tool is more rigid than the thing it's working, right? The metal is malleable, right? So it can be wherever it wants, and the metal gets out of the way. In our world, like everything is harder and stiffer than we are, right? So we don't get to tell the concrete where we are. We don't get to tell trees that we like run into like where we are, right? Like they don't care, right? They're going to be in the way. So there's position control doesn't work, is what I'm saying, because the world is going to be in whatever position it wants, and you have to adapt to that. So the type of control that you actually need to walk, to balance, to tell where the world is called force control. Instead of saying, I'm going to put my hand here, and the tree says, no, you're not, right? You're going to say, I'm going to push with 10 pounds that way, right? And your hand's going to move with 10 pounds of acceleration until it hits something, and then it's going to apply 10 pounds to that thing, right? That is what our balance system is actually like. It's not about where you place your feet nearly so much as it's about how much force you are putting on them at any given time. So the whole problem with robotics is that we started by pulling all of how computer-controlled equipment works, right? We started with machine tools that know the world perfectly and want to execute positions perfectly, and that was the baseline architecture for how to make robots up through now, right? So there's still a whole tool chain of like motor, an encoder, a gear head, you know, like all of this low backlash gearing, timing belts, etc. Those are all meant to control position perfectly, right? But it turns out that's the last thing you want. The first thing that you want is the ability to control force, which is a whole other set of infrastructure that the world didn't realize it needed until about 1985, 1990, when Mark Setrakian started working in the Leg Lab on running robots. So if you look back, if you look at YouTube and you look up like Leg Lab robots, in 1985, Mark Setrakian had robots jumping, trotting, and running around that look a lot like the Boston Dynamics robots of today, except a lot simpler, right? So they're kind of like hopping around, moving, have these amazing displays of dexterity, and then the world was like, oh, that's cute, we don't care, right? We're just gonna continue making our robots the way that we've been making them, like CNC machine tools, and we're gonna hope that that pans out. And then it took the world 20 years to realize, oh, hey, it's not gonna pan out like that. Maybe we should actually look at force-controlled robots to try and make something walk. And now we're finally catching up. So now there's the DARPA Robotics Challenge with giant hydraulic humanoids, or 6-foot-tall hydraulic humanoids that are like helping in disaster response scenarios. Those trials happen in June. It's gonna be super cool. And you have these humanoids suddenly just barely starting to be functional and starting to move around because we suddenly realized, oh, hey, you need a whole other way of designing these robots that's totally different from how we design most machine tools, most robots that exist in the world today. And that's what we're getting.
It is an interesting arrogance of humans that we want our robots to be exactly like us, because bipedal motion is incredibly inefficient. You as a human will trip over stuff sometime today, I can pretty much guarantee. You may not fall flat on your face and break your nose, but you'll be walking along and there's a cable over there and you'll trip over it, but you'll stumble and you'll catch yourself. And as a biped, that's very common for bipeds to do. Whereas if you look at a dog, a quadruped, quadrupeds you really don't see dogs tripping very much. Or then you look at a hexapod, or an octopod like a spider, and they never trip. And so one of the things that you can do is to make humanoids or more or robots that walk is to stop thinking in terms of bipedal motion and start thinking in terms of quadrupeds or hexapods or tripods, which I think Mark has done a very good job of doing.
Well, that's an interesting segue. So now I think, no, this is good. So I'm going to try to connect together the things that Gui and Dave are talking about. Gui is talking about a lot of mistakes that one can make in robotics, and I'm going to show you all the mistakes that I have made. So my name is Mark Setrakian, and my background is I'm a puppeteer. I started out as a puppeteer. I've been making animatronic creatures for Hollywood since 1985, around the time when Mark Raybert was teaching robots to walk. And so my approach has been in the environment of a movie set, making things that look like a creature or look like a person or look like an animal. And as I've gone along through my career, I've been trying to advance that animatronic art, and I've found myself in the world of robotics now. And so as CGI is changing the world of practical effects, I've been upping my game and moving on to other things, other ways of utilizing animatronics or robotics in entertainment. So I guess I'm going to start with just briefly something I worked on a couple years ago called Robot Combat League. So this is exactly what Gui was talking about. This is a position-based robot. So this is a machine that is aware of its position in space. It is able to move. It knows where its limbs are. But this is like a brute force walking machine. And the whole purpose of this thing was to be able to fight in an arena where these machines are going to beat the crap out of each other. So the idea that it could maintain its balance while being pummeled by another one, I just didn't think that I could get that done in 4 months, which is how much time I had to build this thing. So this is for no purpose other than just because it was fun. So I hopped on. And this was really interesting getting on the machine and riding it, because I got that the distance between this thing not being able to balance and being able to dynamically balance isn't that far, because here I am acting as a sensor and I'm acting as like a dynamic load, right? So there's all this weight up in the top, which is the manifold, and it's like a counterweight waiting to be swung around and used to dampen out oscillations. But anyway, that was fun. So
and you could get the sense of size of that robot, that Mark was standing on it, and the robots were about twice as tall as an average human?
No, they were only about 8 feet tall.
8 feet, only about 8 feet tall.
So this is between matches. I'm testing out one of the machines. So you get the idea. These are robots that are controlled by an exosuit, and we had hydraulic leaks all the time, and it was very difficult to keep them in good tune. But they were ridiculously powerful. And I don't have any sound, but this is there it is. Let's just play that again. It's just so satisfying. So this is the first steps. This is one of the 12 Robot Combat League robots taking its first steps. And that was something that was fun. They could actually run across the arena. But anyway, that was since then, I've done a couple of robots, and I want to talk about Axis.
Okay.
So you were talking about hexapods a second ago. So this is a little bit of a diversion from the.
And so I'll intro this is that when you're talking about humanoid robots, you're not just talking about your legs, but your fingers and the ability to manipulate things. Is that what good is it to be able to walk across an arena floor or whatever else if you don't have arms and fingers to grab things and properly manipulate them?
So this is an art piece. It is a mechanical hand, basically, that holds a globe. And as many of you, I hope, know, Dave runs an incredible event called Robogames. And one of the categories of Robogames is the art category, which is right up my alley. So I built this thing as an art piece, and I'm going to go to...
Basically, it's this magnificent 5-foot tall arm and hand, and then the fingers become a jongleur.
Do you like it?
And are spinning a ball in the exact proportion. You can tell which of those is the thumb and which is the four fingers.
Yeah, it's very specifically a hand. So for me, the learning experience on this was learning to do the inverse kinematics to move the fingers in a way that would manipulate a sphere.
That's really like an art piece. That shadow is so cool.
And Dave, I don't think you know this. Since we last saw each other, I made another one.
I saw the one with the silver ball.
I think.
So this one is very much a hand, and it handles a very light weight. I find it kind of mesmerizing to watch, but I know we don't have a lot of time, so let's.
For those who don't know what inverse kinematics is, when you're 2, more or less, you learn how to walk.
And this has a level,
That's when I talked about earlier the kinesthetic sense. You don't really think about how you're walking, ever. It's very, very rare that you think about how you're walking. Even if you're walking uphill, one of the things you automatically do is you adjust the angle that your ankles are at as you're walking uphill, because you want to stay vertical. You don't want to walk uphill like this, so you adjust your angles. And that inverse kinematics is figuring out how to adjust all of your degrees of motion so that you can accomplish what you do. Because if you use a normal walking gait on a flat floor, and then you use that exact same gait to try to walk up a hill, you're going to fall over backwards. You actually have to adjust the angle of your ankles in order to be able to walk up that hill. But it's not a thing you think about anymore, but it's a thing that roboticists have to think about, which is called inverse kinematics, of how do I make that work?
I think it actually even ties into what you were talking about, Guy, about machine tools, where you've got a machine that has to draw a path at a very specific point in space, and that's what these fingertips are doing. They're drawing a path in this circle. Just briefly how it was made, it's 3D printed along with water jet cut parts. It looks a bit like a big dead crab when it's, and it can go pretty fast. So then, like I said, and this is actually perhaps the most important thing. It knows how to party.
All good robots know how to party.
So the second one, so the thing holds a ball, and a ball is actually pretty easy because the fingertips are almost like a cup, and the ball sits in there, and it can't fall out. But I thought if I want to have a flat thing on there and have the fingers manipulate a flat surface, eventually, if I don't really control the location of that, it's just going to sort of randomly find its way off and fall off. So I wanted to make one that could, number one, hold more weight, and number two, handle something flat. So this is the second one. It's somewhat different. It can handle a bit more weight. The layout of the fingers is perfectly symmetrical, so that no one finger holds any more weight than another. It's holding about 26 pounds here.
Although this is one of those things where robots can be, I was going to ask you, can it walk? Can it be upside down?
Well, it has to be able to walk. So this is a pentapod. This is a 5-legged gate. And a few years ago, I made a hexapod, and in the course of doing it, this is a very special episode of the Addams Family right here. I found that I was able to create almost a kind of a universal gait generator that could generate a sensible walking gait for any number of legs, 6 legs, 5 legs, 4 legs, 2 legs. And I've been using variations on that for a while. I found that it didn't, I found that I had made some mistakes when I went to manipulate the ball. It wasn't quite what I expected, which is great. I love finding out that I've done something wrong because then I can fix it.
The one thing for anyone in this room who wants to ever become a roboticist is you have to get very, very, very good about accepting failure, because building a robot, no matter what kind of robot it is, whether it's a wheeled robot, a remote-controlled robot, a walking robot, an artificial intelligence robot, you're going to fail a lot. A lot. And so the people who become good roboticists are the people who can accept that and move on and fix it again and fix it again.
So this thing that's on the screen right now kind of falls into that category. What I wanted to be able to do was not have this flat board, for example, find its way off. And so there's a camera in the palm of the hand. And what we're seeing is there's a dot in the center there, and I'm pushing the thing off center. And now we see that the system is causing the robot to walk and push that dot to the center. And I kind of feel like this is like my version of a line following robot. This is like 8th grade robotics class project. But at the same time, I'm feeling pretty good about where I'm going with this because I'm starting to get into what Gui talks about, which is having sensors, having the ability to sense its location in space and do something about it. This is, you know, I didn't have an engineering education, so there are a lot of things that I think I probably could have been told maybe 20 years ago. But it is fun not really knowing where the box is as far as thinking inside or outside of the box. But
one of the things when roboticists discuss their robots is degrees of freedom, which are basically how many motors you have. And sometimes a motor can have 1 degree of freedom. Sometimes it can actually have 2 if you have a ball joint. So which sort of brings us back to Gui. So how many degrees of freedom are you working with your big MegaBots?
The unit that you'll see out in Maker Faire only has 13 degrees of freedom, but that's actually spread across 20 actuators. So we link a bunch of them together to move at the same time. So the robot has 2 4-degree freedom arms, which have rotary hydraulic actuators in them, and like everything on the MegaBot is ridiculous. Like the leg actuators produce 28,000 pounds of force in extension, and the arm actuators, the shoulder actuator can produce, I'm going to switch units, I apologize, 39,000 inch-pounds of torque. I forget the exact math, but we calculated it at like about 100 of my co-founder Matt's Ford Focuses. Like if you like put 100 Ford Focuses in parallel and drove their axles on the same shaft, that would produce as much torque as 1 shoulder joint in the MegaBot, which is pretty sweet.
One of the things people don't understand when you're trying to replicate the human body, speaking of degrees of freedom, is can anybody here guess how many muscles you have?
500.
580. You have approximately 580 muscles in your body. So people, like, for years when I worked at the university, I worked on humanoids that were between 12 and 18 inches tall to play soccer, and that was the goal, was they were playing soccer. It's a nice 2-dimensional sport. And they'd fall over all the time, and people would be, and people who don't know anything about robots would be like, God, why can't you get this right? And you're trying to recreate something with 580 muscles with 16 muscles, and it's actually very hard to do.
Yep. The final robots will actually have something like 24 degrees of freedom, or slightly more if you start counting all the gun turrets on the body as like each of their own unique degrees of freedom. But each leg is going to have 6 degrees of freedom. So 12 total in the legs, and then everything else is like the torso twisting, the arms, all of that kind of stuff. And then the robot out there is about 24 horsepower. The robots that we're planning on are about 100 to 120 horsepower, 12,000 pounds, 15 feet tall, which is just ludicrous, which is great.
Has anyone been crushed to death yet?
Nobody has been crushed to death, but I don't know.
But the day is early. It's not even 1. Maker Faire goes till what, 7 o'clock? We got time.
6 o'clock. Yeah, well, so basically, like, it's a humanoid robot. It squats down. So, long story. Basically, we built a prototype. We thought we were being smart. We built the torso of the robot and the right arm, and then we put it on a trailer. So we built up this whole little pyramid base, and we're like, what's the maximum shipping regulation? Like, what's the maximum height for all highways? 13'6". So we built a 13'6" high trailer, and we're like, oh, this is great. We'll just hire a shipping company to tow the trailer, and it'll be fine. And then every shipping company we talked to was like, what the heck is that? We are not towing that thing. No, absolutely not. So we ended up towing this thing across the country twice. ourselves because we didn't know any better. So this time we're like, okay, we're going to build a full independent unit. We're going to squat down to less than commercial shipping height so that it can be commercially shipped so we never have to do this again. So we made it 11.5 feet tall when it's squatting and then 15 feet tall when it's standing. Except it turns out driving an 11.5 foot tall, 12,000 pound robot onto a trailer is like the most terrifying thing I have ever done. And it's like, you know, we were working 18-hour days when we came in. So it's like, okay, the truck is here, just go, right? And I'm like sleep-addled. I'm like, okay, I'm just gonna suit up. I'm just gonna drive it. And it's like the robot starts driving up. I'm like, oh God. I'm like 10 feet in the air. I have no seatbelt on. Like, this whole robot's like teeter-tottering as it's like going up on this lowboy trail. I was like, what have I decided to do with my life? Like, what is this? What is this situation?
One common denominator between most people I know in robotics, it's not that they come from an engineering background or an artistic background or any other background. It's that they never asked anybody how to do it, because if they had, everybody would have said that's impossible. So roboticists, as a rule, are very good at doing the impossible.
That's true. It's a good story. So you survived, obviously.
So it turns out getting the robot off the trailer is way harder than getting it on. So we thought it was going to be easier because the lowboy, the way it works, it couldn't be detached at the site we were loading it in, so we had to go up the back, which is a pretty steep angle. On the front, when you set a lowboy down, it's a really shallow angle, except that the guy that we were working with had these really stubby little ramps for the end of the lowboy. So it's like mostly shallow, and then there's a dip. Right, and they didn't tell me this. So I'm like in the robot suiting up, turning it on, and they put these stubby little ramps at the front of the trailer. And so I'm like driving, and then all of a sudden the like front of the tracks go off the end of the truck, and the whole thing like tilts forward. And I'm like,
For a moment, you're in free fall. Right?
for a moment, I'm in free fall as like the tracks haven't touched the ground. And so I just feel the whole robot tipping over, and I see the ground coming up through the cockpit. And I'm like, well, this is it. Okay, goodbye, everyone. I will see you later. And I'm again, without a seatbelt because I'm an idiot, I like brace myself against the cockpit, push against the tubes. I'm like, it's just over. I'll see you all later. And Matt's standing outside just watching the robot like tilt forward. He's like, well, there goes a year of my life. Like it's all. And then it turns out the right thing to do if you're a heavy machinery operator is like you keep driving. Right? If the thing's tipping forward, you keep driving because that centers you back up, and then you're fine. But it's like my life flashed before my eyes. It's like, oh God, just seize up, don't do anything. Okay, yeah, it like rocked back, like 12,000 pounds of machine made a tremendous noise, and then everything was fine.
There's a group, a Bay Area group called Survival Research Labs, who also builds ginormous robots, and I don't know how many of you have ever been to an SRL show.
Band from San Francisco now?
Pretty much.
Yeah, I think they are.
They're
banned.
Mark is banned from a lot of places. And on one occasion, we were doing a show in Berkeley, and we were offloading a truck, and the center of gravity was just way off. And so roboticists also have an incredible lack of common sense. Otherwise, they wouldn't get into this money-sucking hole. And so 12 of us are standing on the back of this robot, leaning backwards to try to shift the center of gravity so we can do the exact same thing of moving this off of the trailer. And my wife is pregnant at the time, and she's on the back. I'm like, no. No. Off.
Same deal. Well, to continue on the... Okay, look, here's my horrible robot mishap story. Just here, hold this. I got to use my hands. So I'm working on. In 1999, I built a robot called Mechadon, which was a battle bot. It was a 475-pound hexapod, which I'm very proud to say was the ring bearer at Dave's wedding. Anyway, this thing was a monster, and I was sleep-addled. I built it in about 4 weeks, and I'm trying to get this thing set up. It's 3 o'clock in the morning. I'm sitting on the floor of the shop. And it runs on gel cells. It's like a 170-volt system. So I'm chaining all these gel cells together, and my friends are sitting around me, and they're sleep-addled as well, and they're just kind of looking kind of dazed. And I'm connect the battery, and I get down to the end, and I forget where I am, and I connect all of the batteries into a dead short. and there's this ball of white, and it was like I don't know, a scene from Akira, like this sort of this sphere, this white sphere, and then it was gone. And I'm looking at my hands, and the Anderson connectors are gone. My hands are black, and I'm not hurt, and the first like 2 inches of the wire is gone, and I kind of look at, I've got these wires, and the Anderson connectors are gone.
They're basically little plastic connectors that surround.
They're
really
not little.
thick-
I mean, we're talking about like a tangible object just vanishing from the face of the earth. So I said I was the wrong thing, and I cut the ends of the wires off and crimped new connectors on and put it together properly, and it worked. But that moment of like the sphere of plasma, anyway. So that's my don't stay up late and connect batteries together, kids. I want to talk about imitating the human body. So you were talking about imitating the human figure, the human body.
Yeah, I think that's vaguely the subject that we were given in the beginning.
All right, whatever. So I've spent like the last 2 years working on this kind of crazy art project. And about a year and a half ago, I shot a video of this thing that went viral on YouTube. You can tell me if you've seen this. So the story is that, and we should have some sound here. The story is that this is an art gallery in New York. It's a major gallery. It's called the David Werner Gallery. I was approached by a New York artist named Jordan Wolfson, and who's having a lot of success in the art world right now. And he wanted to do an animatronic artwork. And he came to me and described what he wanted to do. And I said, that's impossible. Great, I'll do it. And this was its debut in New York. And I can't explain all of what it means, but if you Google creepy, this comes up. Just watch her move for a second. This is where she goes berserk.
Now there's an interesting point as you're watching this video. You'll note that this robot, which otherwise is performing very well in terms of imitating human action, has a carnival mask on. And there's a reason for that, and I will presume it's the usual reason.
Jordan actually can go on for a while explaining the reasons why the mask is there and what the meaning of the mask is. I can't fully explain it.
I'll go into this, whether it's Jordan's actual reasoning or not.
Check this out. She's about to look at she makes eye contact with you. This is the creepiest thing. But sorry, Dave.
It's okay. So in replicating the human form, there's something called the uncanny valley. And if you graph human experience against a replica human form, you actually get a fairly flat graph. So if you're looking at, say, Chewbacca or a stuffed animal or something like that, the human reaction level is very high in terms of liking it, and it's okay and it's acceptable. And so I'm drawing this imaginary graph in the air here, and so it's very high. It's very acceptable. You get to C-3PO. Which is still very high and acceptable and looks like a human. But once you actually make a plastic face, sort of a Madame Tussauds kind of face, all of a sudden, this is also called the zombie effect. As you're graphing this, actual humans' response to that face drops precipitously. And you go from, wow, this is a really cool thing with a Wookiee or C-3PO or a mask kind of thing, to, oh my God, this creeps me out, until you get to the perfect replication of the human face. And that's what's called the uncanny valley. And it's called the uncanny valley because the graph is almost a perfect flat line until just before the end, in which case it drops completely off, goes to the bottom, flat lines, and then comes right back up if you get something perfect.
Yeah.
Please. And one of the reasons for that is you have so many muscles in your face that when Jim Henson's doing Kermit the Frog, it doesn't creep you out because your mind is filling in all of those blanks that, okay, it's basically a sock with a guy in his hand in it. But when you actually try to do a real face, when I smile at you, I'm using so many muscles that you don't even understand that you have to bring up my eyes and shift my ears back a little bit. And it's a pleasant experience. It's actually, you can detect the difference between a lie and a truth by the way people smile. And that's because they're using different muscles when they tell the truth or smile. And so one of the problems with humanoid robots is making a face that won't creep people out, which is why you use cheats such as this of putting on a carnival mask or using C-3PO, which is all metallic and doesn't move, because that doesn't creep you, the viewer, out as much as trying to actually use artificial skin. Because when you're looking at this dancer, her thighs, there's enough to her thighs to make it look like a real thigh. But there's not ever going to be enough, well, not ever, but not for a long time, to have enough control of the cheek muscles and the eye muscles and the ear muscles and all of the muscles around your mouth to make it feel like a real human. And that creeps you out, which is why when you watch zombie movies, the directors always say, okay, don't move your face. And if you've ever noticed this about zombie movies, and when you play zombie, you may not even realize you're doing it. You stop moving your facial muscles. You go, same thing with Frankenstein. And Mark will now prove me wrong.
No. You just were talking about mechanical faces, and I just so this is one of the weird areas where robotics and creature effects have some interesting crossovers. I totally did not intend to bring this up today, but Dave, since you're talking about faces and even specific muscle groups, this is a character from a movie called Hansel and Gretel Witch Hunters, and it doesn't have 120 muscles, but it has a lot of artificial muscles in the skin that are doing things like drawing in the skin around the eyes, drawing in the nasolabial folds. It actually has nostril flare as well.
And this looks amazingly good. I think this is why you continually don't get nominated for Oscars, because they always think your stuff is CGI.
They don't give Oscars for stuff like this, but I personally find this rather charming. But it helps. If he's ugly, you actually are a little more forgiving. Notice the chin.
Right on cue. Yes, exactly. Well, we didn't mean to call you ugly. Ugly is relative, okay? It's
Huh. Well.
Yeah, I know.
Anyway, so. Oh. Huh? I think he was about to say something that begins with the letter F.
Feelings?
Sure.
So, we've got 7 more minutes before a Q&A. So in those 7 minutes, what would you guys say is the hardest thing about robotics and the most rewarding thing about robotics?
I would say the absolute hardest thing about kind of designing and building a robot from scratch is just like there are literally thousands of things that have to go right in order to pull off a robot. Like there's 100 hydraulic hoses that we crimped ourselves in the MegaBot. There's like at least several hundred feet of sensor wire that has like hundreds of crimp connections on it. And the thing is that like unless you're NASA, unless you have years and years and years and tons of budget to make redundant systems, you basically get one shot across your entire electrical system, across your entire hydraulic, pneumatic, whatever system. And if any one connection goes bad, usually your entire robot dies or acts in a way that's really terrifying, really unsafe, or just not what you want. All of the above sometimes. So getting a robot right, like even when you guys maybe start at the Arduino scale, like one jumper wire popping out of an Arduino in a way that's not immediately visible may cause your entire system to just go down and you have no idea what's wrong for like
or to
a couple
operate
days.
in a way totally unexpected and
Right.
do weird things.
Right. And it's just like just having the mindset of like, okay, I'm focused on my individual task, but I have to get every single tiny little detail right in order for this to work at all, it's hugely time consuming. It's a very specific skill set. The most rewarding thing though is like when these things move, when it just like gets up and moves on its own, it's like, well, I have created life. That's just how it works. Like the thing moves, it looks amazing. Like there are so few, I have created something that the world has never seen before, right? And it moves. And it looks like a creature, and it's just like, it's so incredibly empowering and so much fun. And like, I mean, like right now, like the thing that I want to do, we just finished this robot and I want to go for a joyride somewhere. So like, you'll probably see us in the news with like 80 cop cars traveling along behind us at 2 miles an hour. It'll be like a really crappy take of the Blues Brothers as we like go over a bridge and then into the water.
It'll be the O.J. Simpson slow speed follow.
Right, it's the low speed car chase, except it's a low speed robot chase. Well, everything you just said is it. I mean, the complexity of robotics is actually one of the things that draws me to it, because it's a little bit of everything. Actually, it's a lot of everything. The thing that's actually on the screen right now is this is the first time that I've spent more time working on the software than I did on the hardware, and it's that constant challenge. It's that constant forcing me to learn new things just to get a basic idea to work. Is what I find exciting about it. And just like you said, the thrill of bringing the thing to life and having it start moving. It's nothing else like it, really.
I would say that robotics is not a science unto itself. It is the epicenter of all other sciences. There's mechanical engineering, electrical engineering, computer science, and definitely art, all involved in those. There's kinesthetics. There's all sorts of things that you don't think about when you first start getting into robots. When I got into robots, I was building 500-gram sumo robots with 2 sensors and 2 motors, and all they did was go straight, try to find another thing which was a given to be the other robot, or see the line on the edge. I'd come from a software background where I'd been a professional programmer for many years, but I wanted to get into hardware and do a robot, and I found that incredibly hard. And to Guy's point, if you're not NASA and you can't build 10 redundant systems so that if one fails, it's surprising how frustrating it can be when something goes wrong. I taught computer engineering at San Francisco State University for many years, and the example I would always give on the first day for my freshman class was a car that I used to own, which was a Volkswagen GTI. And to some extent, cars are, mini robots, especially nowadays. I mean, they can park themselves. And one of the things this GTI did was it automatically balanced the fuel-air mix for driving, for optimizing your gas mileage. And inside of the engine, it had a temperature sensor, which isn't your normal thermostat, that's your engine's overheating, but it was a specific temperature sensor to regulate the fuel-air mix. So depending on how hot it was specifically, it would give more or less fuel, more or less air. And this particular model GTI had a problem with it, is the temperature sensor, because it's inside the actual valves, they die. But the programmer was a bad programmer of this car, and what would happen is when the sensor would die, it would presume that because the sensor was reading 0, that the car was an absolute 0, like 0 degrees Kelvin. So there was a car floating out in space. So it should push in a whole bunch of air and not very much fuel, and the car would stall. And so the car would go for like 6 blocks, stall. You'd have to wait half an hour. The car would go for 6, it'd start again, you'd go for 6 blocks. And so one of the things you learn in building robots is presume sensors and motors will fail and program around that. Because what should have happened is when the guys at Volkswagen programmed this car, is that when they saw that sensor fail, sensor reading 0, that is outside of the acceptable range. Here is the acceptable range. The acceptable range is, round figures, 1,000 degrees Fahrenheit to 5,000 degrees Fahrenheit. Oh, we're reading 0 degrees Kelvin, so that's outside of the acceptable range, so I'm just going to feed it this fuel air mix, which is a nominal fuel air mix, it won't optimize fuel efficiency, but the car will work. And this is a problem you will often encounter in robots is, oh, my sensor for my arm, we have them. We have them built in. You know when your arm is all the way here. If the sensor goes bad, the arm may keep trying to fold past the point of your elbow, and then eventually it will break itself. Or if you're trying to move an object, you know when the object is too heavy to push against. The robot may not know that, so you have to program that in.
This is why robots have to feel pain. I'm not kidding. They have to be able to sense. And yeah, when something's wrong, exactly.
So we're at the 10-minute point, so please ask us questions. Don't be afraid.
I guess just come up to the mic.
Please, come up to the mic. Just
Fan of all the robot challenges. Just curious, is there any plans in the works for a new televised series? Like the robot challenges?
Well, there's actually BattleBots is going back into production next week,
Okay.
and so that's coming to ABC. And actually, if you want to go to BattleBots, there are still there's tickets, but
Thursday or Friday.
I was actually given a code, so if you want to enter it, but access.
Robogames, which we shoot, which is 54 different competitions. If you go to robogames.net, we're releasing a DVD of the show that we did last month. And so that'll actually probably end up being a 4-hour DVD covering everything, because Robogames doesn't just do combat robots, but we also do bartending robots. We do, there's 8 different kids events with Lego robots, there's sumo robots, there's soccer playing robots, there's all sorts of things. Is your show available anywhere on DVD or anything?
I think you can watch RCL I watch it on iTunes, and I think you can
So
see
iTunes,
see
Robot
episodes
Combat
on
League.
YouTube as well.
And keep your eyes peeled for a show or two about MegaBots coming up in the future.
Yeah, it's one of those things where the culture of entertainment is shifting, and YouTube is your better option for finding really cool robot stuff. There's a website called Robots Dreams, robots plural, dreams plural.com, which is an excellent website for getting up-to-date videos. He's got new videos every day of what's cool in robotics. Everything from a drone to a humanoid to a combat robot to a bartending robot to whatever.
Next question.
It's particularly so.
Closer to the mic.
Oh, sorry. Okay. Have you had any projects by supervisors, everything, where the goalposts kept moving just incrementally, and then sometimes if that happened, how would you deal with that, particularly in a complex robot? And have you ever said no, this goalpost is too far and you have to compromise?
Most of my experience has been working for DARPA or very specific high standards of we have to show a humanoid robot by Maker Faire. So it's not usually that the goalposts change, it's that they're so far away, it's just oh my God, okay. I just need to step up and just keep going. So for me, it's been more pushing harder than I thought was possible. To actually achieve really, really, really far away goalposts, which I think is honestly more satisfying in some ways than accomplishing a little thing and then accomplishing another little thing and then so on and so forth. But I'm also a masochist, so don't take my word for it.
Roboticists tend to be masochists, or at least have a very high tolerance for pain.
Yeah, or have some kind of sleep disorder.
Yeah.
So,
OCD.
yeah, in my world, the goalposts do move quite often, and the response is the same. You just work harder. You work harder, you put more time into it, and that's basically what it comes down to, is just this stuff takes a lot of work and a lot of time, and if you're not willing to put that in, it's probably not going to work out.
One of the primary reasons I founded Robogames was to do exactly that, is nothing makes you work harder, in my opinion, than losing and coming in second place. Is that whether you're competing at Robogames in the cocktail robot division, or the combat division, or the soccer division, or the sumo division, if you come in second, man, that sucks. You want to be first. You want the gold medal. You don't want the silver medal, so you work harder. And we started Robogames in 2004, and in those 11, 12 years, definitely people have pushed those goalposts, and they push them themselves, because you see Mark do this incredible thing with fingers spinning a ball, and you want to do better. I mean, I got a nasty email from a local college professor about how the Mexican college teams just kick their butts every year in sumo, and he's like, well, there should be two divisions, and my reply to him was like, no, you should work harder to beat the Mexican guys who are obviously putting more time into it than your students. The goalposts are always moving, because, I mean, whether it's for a financial gain, which is to say you're making a drone, but so is he, and so is he, and all of these companies are making drones. Well, you want to sell more drones than they sell, so the goalposts are moving that you have to make a better drone that's cheaper, that has more functions or functionality, or whether it's something like a robot competition where you want to win. And the best part about going to robot competitions, and not just mine, but any robot competitions, and things like Maker Faire, is you see stuff that inspires you to do better in your own work, things that you never thought of. I call it the Roger Bannister effect, which is, Roger Bannister, for those who don't know, was the first person to run a 4-minute mile. Prior to Roger Bannister, it was known absolutely that the human body could not run a mile in less than 4 minutes. It was not possible. Since then, several hundred people have done it. The barrier was psychological. Getting humanoids to move, getting humanoids to look this realistic, getting humanoids to be able to walk was absolutely impossible until Sony put in a buttload of money to get Asimo to work on a regular basis and actually walk across the stage. And then people said, oh, it's possible. And now you can buy for $400 an 18-inch tall humanoid by several different companies that do a fairly good job of walking on a flat surface, and if they do fall down, they have IMUs built into them that they can then stand up. So, in answer to your question, the goalposts are always moving. They never sit still.
Okay, thank you. I have a question over here. Maybe for my own sake, but for others in the audience, can you guys just go through what is the DARPA Robotics Challenge, and when is it, and where is it? And
there are actually several. One of them is the Humanoid Challenge.
So I believe it's June 5th and 6th, DARPARoboticschallenge.com or something similar to that. It's basically 6-foot-tall humanoid robots competing in an event inspired by the Fukushima disaster, where basically this was the shining light for robots. It's like, oh, hey, we have this rubble-ridden disaster zone that needs, robots to go in and turn valves and do all sorts of stuff, and then every single robot we'd made to date fell flat on its face and didn't work. Because turns out, like, a little bit of rubble in a doorway stops some robots cold, right? Or like the ability to turn a valve requires a hand that hadn't been developed strong enough yet. So the DRC, this is Atlas. This is one of so there will be 10 Atlas humanoid robots. They're all hydraulic, made by Boston Dynamics, now Google Robotics. In the competition, in addition to a couple of other robots, and they will be in a Fukushima-like environment, doing things like opening doors, using tools. You can see it live, I believe, in Pomona. Pomona, June 5th and 6th, there will be lots of live streaming. I will offer no guarantees as to how entertaining it's going to be. It's probably going to be like watching paint dry slowly in robot form.
There'll be a pavilion there. There'll be like stuff to look at. It won't be intensely boring, but it'll be. I think it'll be. I'm going, and it's.
Speaking of the goalposts,
it's free also.
And the DARPA challenge. The first DARPA challenge was the DARPA Grand Challenge, which was an autonomous vehicle challenge, where the vehicles were originally they were intended to go from downtown LA to downtown Vegas. I talked them out of that. I was one of the consultants, and it was a much shorter course, and it ended up being about a 45-mile course. The first time they did it, no vehicle made it further than 7 miles without stopping. So getting back to that Roger Bannister
some of them were on
effect.
fire when they stopped.
And some of them were on fire when they stopped, yeah. So getting back to the Roger Bannister effect, like it's impossible. The second year they do it, 3 vehicles finished the course. And actually, the winner was Stanford with a hairline budget where they were given basically a garage, and VW donated a car, and everything else was done nothing. Whereas Carnegie Mellon University, threw tens, if not hundreds of millions of dollars at brute forcing solutions to this. And Red's team at CMU lost to this scrappy little division at Stanford, which also speaks to the money involved in robotics. Is one of the things I've seen at Robogames is I've seen people make $75,000 combat robots in the 220-pound division and lose to people who spent $500-600 on their robots. So money isn't the end-all be-all of success in robots. The end-all be-all of building a successful robot is don't give up, don't quit, keep working. And one of my favorite expressions is the difference between good and great is 3 hours a day.
Well, on that note, I think we've just had the Roger Bannister effect of Maker Faire panels. This was one of the best I've ever heard. Thank you so much.
Thank you.
Thanks, everyone.